Hello everyone, welcome to lecture 1 of CSC 811, and lecture 1 is about machine learning basics. The learning objectives of this lecture are a brief overview of machine learning, key terminologies in machine learning, 3 key tasks in machine learning, 4 why do we need to learn about machine learning, and 5 why Python is so great for machine learning. What is machine learning? Machine learning is actively being used today, perhaps in many more places than you'd expect. Here's a hypothetical day, and many times you'll encounter machine learning. For example, you realize it's your friend's birthday and want to send her a card via an email. You search for funny cards, and the search engine shows you the 10 most relevant links. You click the second link, the search engine learns from this. Next, you check some mail, and without you noticing it, the spam filter catches unsolicited ads for pharmaceutical and places them in the spam folder. Next, you head to the store to buy the birthday card. When you are shopping for the card, you pick up some diapers for your friend's child. When you get to the checkout and purchase the items, the human operating the cash registers you a coupon for birthday cards. The cash registers software generated this coupon for you based on the preference of you normally buying cards and diapers. You send the birthday card to your friend, and a machine at the post office recognizes your handwriting to direct the mail to the proper delivery truck. Next, you go to the loan agent and ask them if you are eligible for loan. They don't answer, but plug some financial information about you into the computer, and a decision is made. Finally, you head to the casino for some late-night entertainment, and as you walk in the door, the person walking in behind you gets approached by security, seemingly out of nowhere. They tell him, "Sorry, Mr. John, we're going to have to ask you to leave the casino. You have been counted as a red flag." In all of the previously mentioned scenarios, machine learning was present. Companies are using it to improve business decisions, increase productivity, detect disease, forecast weather, and do many more things. With the exponential growth of technology, we not only need better tools to understand the data we currently have, but also need to prepare ourselves for the data we will have. Are you ready for machine learning then? In this chapter, you'll find out what machine learning is, where it's already being used around you, and how it might help you in the future. Next, we'll talk about some common approaches to solving problems with machine learning. Last, you will find out why Python is so great and why it's a great language for machine learning. Then we'll go through a quick example using a module for Python called NumPy, which allows you to abstract and matrix calculations. So, to answer the question, what is machine learning? In all but the most trivial cases, insight or knowledge you're trying to get out of raw data won't be obvious from looking at the data. For example, in detecting spam email, looking for the occurrence of a single word may not be very helpful. But looking at the occurrence of certain words used together, combined with the length of the email and other factors, you could get a much clearer picture of whether the email is spam or not. Machine learning is turning data into information. Machine learning lies at the intersection of computer science, engineering, and statistics, and often appears in other disciplines. As you'll see later, it can be applied to many fields from politics to geosciences. It's a tool that can be applied to many problems. A field that needs to interpret and act on data can benefit from machine learning techniques. Machine learning uses statistics. To most people, statistics is an esoteric subject. When we say esoteric, that means intended for or likely to be understood by a set of people who are specialized in that area. So to most people, statistics is an esoteric subject used for companies to lie about how great their products are. So why do the rest of us need statistics? The practice of engineering is applying science to solve a problem. In engineering, we used to solving a deterministic problem where our solution solves the problem all the time. If you are asked to write software to control a vending machine, it had better work all the time regardless of the money entered or the buttons pressed. There are many problems where the solution isn't deterministic. That is, we don't know enough about the problem or don't have enough computing power to properly model the problem. For these problems, we need statistics. For example, the motivation of humans is a problem that is currently too difficult to model. In social sciences, being right 60% of the time is considered successful. If you can predict the way people will behave 60% of the time, we're doing well. How can this be? Shouldn't we be right all the time? If you're not right all the time, doesn't that mean that we're doing something wrong? Let me give an example to illustrate the problem for not being able to model the problem fully. Do humans not act to maximize their own happiness? Can't we just predict the outcome of the events involving humans based on this assumption? Perhaps, but it's difficult to define what makes everyone happy, because this may differ greatly from one person to the next. Even so, if our assumptions are correct about people, maximizing their happiness, the definition of happiness is too complex to model. There are many other examples outside human behavior that we can't currently model deterministically. For these problems, we need to use some tools from statistics. In the last half of the 20th century, the majority of the workforce in the developed world has moved from manual labor to something known as knowledge work. The clear definitions of move this from here to there and put a hole in this are gone. Things are much more ambiguous now. Job assignments such as maximize profits, minimize risk, and find the best marketing strategy are all too common. The fire hose of information available to us from the World Wide Web makes the jobs of knowledge workers even harder. Making sense to all the data with our job in mind is becoming more essential skill. With so much economic activity dependent on information, you can't afford to be lost in the data. Machine learning will help you get through all the data and extract some information. So we need to go over some vocabulary that commonly appears in the machine learning so it's clear what's being discussed in this lecture. Key terminologies. Before we jump into machine learning algorithms, it would be best to explain some terminology. The best way to do so is through an example of a system someone may want to make. We'll go through an example of building bird classification system. This sort of system is an interesting topic often associated with machine learning called expert systems. By creating a computer program to recognize birds, we've replaced an ornithologist with a computer. The ornithologist is a bird expert, so we've created an expert system. In table 1.1 are some values for 4 parts of birds that we decided to measure. We chose to measure weight, wingspan, whether it has webbed feet, and the color of its back. In reality, you want to measure more than this. It's a common practice to measure just about anything you can measure and sort out the important parts later. The 4 things we have measured are called features. These are also called attributes, but we'll stick to them with the term features in this lecture and throughout this course. Now, each of the rows in table 1.1 is an instance made up of features. Remember, each of the row is called an instance. The first two features in table 1.1 are numeric and can take on decimal values. The third feature, webbed feed, is binary. It can only take 1 or 0. The fourth feature, back color, is an enumeration over the color palette we're using, and I just chose some very common colors. We ask the people doing the measurements to choose one of the 7 colors, then back color would be an integer. One task in machine learning is classification. Let's illustrate this in the table 1.1, and the fact that the information about the ivory-billed woodpecker would get us $50,000. Let's say for an example. We want to identify this bird out of a bunch of other birds, and we want to profit from this. We could set up a bird feeder and then hire an ornithologist, a bird expert, to watch it, and when they see an ivory-billed woodpecker, they would give us a call. This would be expensive, and the person could only be in one place at a time. We could also automate this process, set up many bird feeders with a camera and computers attached to them to identify the birds that come in. We could put a scale on the bird feeder to get the bird's weight and write some computer vision code to extract the bird's wingspan, feed type, and back color. For the moment, assume we have all that information. How do we then decide if a bird at our feeder is an ivory-billed woodpecker or something else? This task is called classification, and there are many machine learning algorithms that are good at classification. The class in this example is a bird species. More specifically, we can reduce our classes to ivory-billed woodpecker or everything else. So we've decided on a machine learning algorithm to use for classification. What we need to do next is train the algorithm or allow it to learn. To train the algorithm, we feed it quality data known as training set. A training set is the set of training examples we use to train our machine learning algorithms. In table 1.1, our training set has 6 training examples. Each training example has 4 features and 1 target variable. This is depicted in figure 1.2. The target variable is what we'll be trying to predict with our machine learning algorithms. In classification, the target variable takes on a nominal value, and in the task of regression, its value could be continuous. In a training set, the target variable is known. The machine learns by finding some relationship between the features and the target variable. The target variable is the species, and as I mentioned earlier, we can reduce this to take nominal values. In the classification problem, the target variable are called classes, and there is assumed to be a finite number of classes. Do note that features or attributes are the individual measurements that, when combined with other features, make up a training example. This is usually columns in a training or test set. To test machine learning algorithms, what's usually done is to have a training set of data and separate data set, called a test data set or test set. Initially, the program is fed the training examples. This is when the machine learning takes place. Next, the test set is fed to the program. The target variable for each example from the test set isn't given to the program, and the program decides which class each example should belong to. A target variable or class that the training example belongs to is then compared to the predicted value, and we can get a sense of how accurate the algorithm is. There are better ways to use all the information in the test set and training set. We'll discuss them later. In our bird classification example, assume we have tested the program and it meets our desired levels of accuracy. Can we see what the machine learning has learned? This is called knowledge representation. The answer is it depends. Some algorithms have knowledge representation that's more readable by humans than others. The knowledge representation may be in the form of a set of rules. It may be a probability distribution or an example from the training set. In some cases, we may not be interested in building an expert system, but interested only in the knowledge representation that's acquired from training a machine learning algorithm. We've covered a lot of key terms in machine learning in this lecture. Let's briefly have a look at these. We've looked at features, attributes, instances, classification, class, training set, target variable, test data, knowledge representation. Try to find the definitions for these and learn them. Key tasks of machine learning. Now we'll outline the key jobs of machine learning and set a framework that allows us to easily turn a machine learning algorithm into a solid working application. The example previously covered was for the task of classification. In classification, our job is to predict what class an instance of data fall into. Another task in machine learning is regression. Regression is the prediction of a numeric value. Most people have probably seen an example of regression with a best fit line drawn through some data points to generalize the data points. Classification and regression are examples of supervised learning. This set of problems is known as supervised because we're telling the algorithm what to predict. The opposite of supervised learning is a set of tasks known as unsupervised learning. In unsupervised learning, there's no label or target value given for the data. A task where we group similar items together is known as clustering. In unsupervised learning, we may also want to find statistical values that describe the data. This is known as density estimation. Another task of unsupervised learning may be reducing the data from many features to a small number so that we can properly visualize in it 2 or 3 dimensions. Table 2 lists some common tasks in machine learning with algorithms used to solve these tasks. If you notice, Table 1.2, that multiple techniques are used for completing the same task. You may be asking yourself, if these do the same, why are there 4 different methods? Why can't I just choose one method and master it? I'll answer that question next. How to choose the right algorithm. With all the different algorithms in table 1.2, you can choose which one to use. First, you need to consider your goal. What are you trying to get out of this? Do you want a probability that it might rain tomorrow? Or do you want to find groups of voters with similar interests? What data do you have or can you collect? Those are the big questions. Let's talk about your goals. If you're trying to predict or forecast a target value, then you need to look into supervised learning. If not, then unsupervised learning is a place where you want to be. If you have chosen supervised learning, what's your target value? Is it a discrete value like yes or no, or like 1, 2, 3, or A, B, C, or red, yellow, black? If so, then you want to look into classification. If the target value can take on a number of values, say any value from 0.00 to 100.0, or any value from negative 999 to 999, or positive infinity to negative infinity, then you need to look into regression. If you're not going to predict, or if you're not trying to predict a target value, then you need to look into unsupervised learning. Are you trying to fit your data in some discrete groups? If so, and that's all you need, you should look into clustering. Do you need to have some numerical estimate of how strong the fit is into each group? If you answer yes, then you probably should look into density estimation algorithm. The rules I've given here should point you in the right direction, but are not unbreakable laws. We'll see later on how you can use classification techniques for regression, blurring the distinction that we have made earlier with supervised learning. The second thing you need to consider is your data. You should spend some time getting to know your data, and the more you know about it, the better you will be able to build a successful application. Things to know about your data are the features nominal or continuous? Are there missing values in the features? If there are missing values, why are there missing values? Are there outliers in your data? Are you looking for a needle in a haystack? Something that happens very infrequently? All of these features about your data can help you narrow the algorithm selection process. With the algorithm narrowed, there's no single answer to what the best algorithm is or what will give you the best results. You're going to have to try different algorithms and see how they perform. There are other machine learning techniques that you can use to improve the performance of a machine learning algorithm. The relative performance of two algorithms may change after you process the input data. We'll discuss these in more detail later, but the point is that finding the best algorithm is an iterative process of trial and error. Many of the algorithms are different, but there are some common steps you need to take with all of these algorithms when building a machine learning application. Let's have a look at these steps in the next slide. Our approach to understanding and developing an application using machine learning in this course will follow a procedure similar to what you see in the slide. One will collect data. You could collect the samples by scraping a website and extracting data, or you could get information from an RSS feed or an API, application processing interface. You could have a device collect wind speed measurement and send them to you, or blood glucose levels, or anything you can measure. The number of options is endless. To save some time and effort, you could use publicly available data. Once you have this data, you need to make sure it's in a usable format. The format we'll be using in this course is the Python lists. We'll talk about Python more in a bit. The benefits of having this standard format is that you can mix and match algorithms and data sources. You may need to do some algorithm-specific formatting here. Some algorithms need features in a special format. Some algorithms can deal with target variables and features as strings, and some need them to be integers. We'll get to this later, but the algorithm-specific formatting is usually trivial compared to collecting data. 3, analyze the input data. This is looking at the data from the previous task. This could be as simple as looking at the data you've passed in a text editor to make sure steps 1 and 2 are actually working, and you don't have a bunch of empty values. You can also look at the data to see if you can recognize any patterns or if there are anything obvious, such as a few data points that are vastly different from the rest of the set. Plotting data in 1, 2, or 3 dimensions can also help, but most of the time you'll have more than 3 features, and you can't easily plot the data across all the features at one time. You could, however, use some advanced methods we'll talk about later to distill multiple dimensions down to 2 or 3 so you can visualize the data. 4, cleaning. If you're looking with a production system and you know what the data should look like, you must trust its source. You can skip this step. This step takes human involvement, and for an automated system, you don't want human involvement. The value of this step is that it makes you understand you don't have garbage coming in, because garbage in is usually equals to garbage out. 5. Train the algorithm. This is where the machine learning takes place. This step and the next step are where the core algorithms lie. Depending on the algorithm, you feed the algorithm good, clean data from the first two steps and extract knowledge or information. This knowledge you often store in a format that's readily usable by a machine for the next two steps. In the case of unsupervised learning, there's no training step because you don't have a target value. Everything is used up in the next step. And the next step is test the algorithm. This is where the information learned in the previous step is put to use. When you're evaluating an algorithm, you test it to see how well it does. In case of supervised learning, you have some known values you can use to evaluate the algorithm. In unsupervised learning, you may have to use some other metrics to evaluate success. In either cases, if you're not satisfied, you can go back to step 4, which is cleaning. Change some things and try testing again. Often, the collection or preparation of data may have been the problem, and you'll have to go back to step 1. 7, and the last step, use it. Here, you make a real program to do some tasks, and once again, you see if all the previous steps worked as you expected. You might encounter some new data and have to revisit steps 1 to 5. Now, we'll talk about a language to implement machine learning algorithms. We need a language that's understandable by a wide variety of people. We also need a language that has libraries written for a number of tasks, especially matrix math operations. We also would like a language with an active developer community. Python is the best choice for this reason. Why use Python? Python is a great language for machine learning for a number of reasons. First, Python has clear syntax. Second, Python makes text manipulation extremely easy. A large number of people in organizations use Python, so there's ample development and documentation. Now, let's have a look at a few more elements related to Python and why Python should be used. Executable pseudocode. The clear syntax of Python has earned it the name executable pseudocode. The default install of Python already carries high-level data type like lists, tuples, dictionaries, sets, queues, and so on, but you don't have to program it yourself. These high-level data types make it abstract concepts easy to implement. With Python, you can program in any style you're familiar with: object-oriented, procedural, functional, and so on. With Python, it's easy to make progress, and it's easy to process and manipulate text, which makes it ideal for processing non-numeric data. You can get by in Python with little to no irregular expression usage. There are a number of libraries for using Python to access web pages, and the intuitive text manipulation makes it easy to extract data from HTML. Python is popular. Python is popular, so lots of examples are given, which makes learning it fast. Second, the popularity means that there are lots of modules available for many applications. Python is popular in the scientific and financial communities as well. A number of scientific libraries such as SciPy and NumPy allow you to do vector and matrix operations. This makes the code even more readable and allows you to write code that looks like linear algebra. In addition, the scientific libraries SciPy and NumPy are compiled using lower-level languages, C and Fortran. This makes doing computations with these tools much faster. Therefore, we will be using NumPy in this course. The scientific tools in Python works well with plotting tool called matplotlib. Matplotlib can plot 2D and 3D and can handle most types of plots commonly used in scientific world. We'll be using matplotlib extensively throughout this book. And throughout this course. Python also has an interactive shell, which allows you to view and inspect elements of the program as you are developing it. Next is Python has the other languages you don't. There are high-level languages that allow you to do matrix math such as MATLAB and Mathematica. MATLAB has a number of built-in features that make machine learning easier. MATLAB is also very fast. The problem with MATLAB is that to legally use it, it will cost you a few $1,000s. There are third-party add-ons to MATLAB, but nothing on the scale of an open source project. There are matrix math libraries for low-level languages such as Java and C. The problem with these languages is that it takes a lot of code to get things done in a simple way. First, you have to typecast variables, and then with Java, it seems that you have to write setters and getters every time you sneeze. Don't forget subclassing. You have to subclass methods even if you aren't going to use them. At the end of the day, as you have written a lot of code, sometimes tedious codes to do simple things. This isn't the case with Python. Python is clean, concise, and easy to read. Python is easy for non-programmers to pick up. Java and C aren't so easy to pick up and much less concise than Python. Perhaps one day, we can see people using Python way more than the other languages. Python is a higher level language. This allows you to spend more time making sense of data and less time concerned with how machine approximates the data. Python easily allows you to effortlessly express yourself. Just like each and everything, some things have their drawbacks. Everything has their drawbacks, sorry. So some of the drawbacks of Python include, the only drawback rather, of Python is that it's not as fast as Java or C. You can, however, call C-compiled programs from Python. This gives you the best of both worlds and allow you to incrementally develop a program. If you experiment with an idea in Python and decide it's something you want to pursue in a production system, it will be easy to make the transition. If the program is built in a modular fashion, you could fast get it up and running in Python, and then to improve speed, start building portions of the code in C. The Boost C++ library makes this easy to do. Other tools such as Cython and PyPy allows you write typed versions of Python with performance gains over regular Python. If an idea for programming, if an idea for a program or application is flawed, then it will be flawed at low speed as well as high speed. If an idea is a bad idea, writing code to make it fast or scale to a large number of users doesn't change anything. This makes Python so beautiful that you can quickly see an idea in action and then optimize it if needed. Now that you know the languages, now that you know the language you're going to use, I'm sure you're ready to start using it. In our lab class, we'll walk through the use of Python shell and NumPy. If you want to practice the lab before our lab class, refer to the textbook to pages 15, 16, and 17. Summary. Machine learning is already being used in our daily lives. even though you may not be aware of it. The amount of data coming at you isn't going to decrease, and being able to make sense of all this data will be an essential skill for people working in a data-driven industry. In machine learning, you look at instance of data. Each instance of data is composed of a number of features. Classification, the popular and essential task of machine learning, is used to place an unknown piece of data into a known group. In order to train or build a classifier, you feed it data for which you know the class. This data is called a training set. Now we have in our earlier slides, we have looked at recognizing birds through our expert system. But building a machine with accuracy close to that of a human expert could greatly increase the quality of life. When you build software that can match the accuracy of a human doctor, people can more rapidly get treatment. Better prediction of weather could lead to fewer water shortages and greater supply of food. The examples where machine learning could be useful are endless. Now, in our next lecture, we'll introduce to our very first machine learning algorithm. This will be an example of classification, which is a type of supervised learning. Till then, all the best for the week. See you in the class. Thank you.